Hello everyone, today let's take a look at Quantipose number 55 where it gets a little bit more complicated of a combinatorics question. Basically we have 5 letters and 5 envelopes, each labeled 1 through 5. The letters are randomly placed, 1 per envelope, and then what is the probability that no letter ends up in the envelope with the same number? So here is essentially our setup. Here are 5 letters, and then up top are our 5 envelopes, and they're all numbered. So this one is meant to go into this one, and number 2 is meant to go here, and so on. And this is just one example of none of the letters ending up in the same envelope in case it was unclear. And this setup here is called a derangement when none of the numbers end up in the spot that they're supposed to. And we know that in combinatorics, when we need to calculate something, we need the number of total outcomes on the bottom of our fraction, and on the top, we need the number of restricted outcomes. In this case, it's the number of derangements of 5 numbers. And the total is just the permutations of 5 objects, right? I can place number 1 in any of the 5 envelopes. Once I do that, there's going to be 4 spaces left for number 2, and etc. So it's going to be 5 factorial total ways to place these letters in the envelopes. Now the tricky part is going to be calculating the number of derangements. First, let's just understand that the number of derangements is the number of permutations where the letter's not in the correct envelope. So that's just also equal to the total number of possible permutations minus the number where we have at least one in the correct envelope. So I just wrote out the words here. This is 120, the total, minus the permutations with at least one letter in the correct envelope. That makes sense. And let's just define these variables A1, A2, A3, A4, A5. So A1 would be the set of permutations with a letter 1 in the correct envelope, and etc. So A3 would be the number of permutations with a letter 3 in the correct envelope. And then if we do that, we can change this term and we can represent it in set notation as the magnitude of A1 union A2 ... union all of these up to A5. So now what does this term actually mean? Well, if you remember from sets, I'll just draw out the Venn diagram one more time with only 3 A's, so it's a little bit easier to visualize. So here I just drew out the 3-letter example to make it easier to visualize. And for our 6 permutations, we have these right here, right? 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. These are all the permutations we could have in the 3-letter case, right? Where 1 is in its correct spot here. If it's in the first position, that just corresponds to the letter being in the correct envelope, right? This is what it would look like if you filled in the Venn diagram with all these permutations down here, right? Like 1, 2, and 3 in the center, because every single letter would be in the correct envelope in this case. 1, 3, 2 is over here because only the first letter is in the correct envelope, right? 3 and 2 are switched. And what are these over here? Well, these are our derangements where no letter is in the correct envelope, which is what we are trying to find. So the way that we calculate derangements, as we showed earlier, was you take the entirety of what's in this box, or the total, and you subtract the union of all these A's, right? Everything inside of here, and that's when you find these, the derangements. And in the 5-letter case, this is what we're trying to find here, so we could subtract it from the total. So let's dive into solving this. So let's go back to our letter diagram over here. So now let's see how we could go about calculating something like A1. Well, let's just put letter 1 in its correct envelope, and then we have 4 letters remaining to place in these envelopes. So we have 4 factorial permutations of ways to place them in. So we could say the magnitude of A1 is going to be equal to 4 factorial, which is 24. Now let's see what A2 is, right? If we fix A2, then we can permute these 4 in any way we want. So we have 4 factorial ways to do that. So the magnitude of A2 will also be equal to 24. And obviously A3 and A4 and A5 will also have magnitude 24. But the key thing to notice is that these are obviously not disjoint sets, right? They have overlap, right? When I fixed 1 in place and I permuted these 4, well, 6 of these 24 permutations had 2 also fixed in place. And then in the future, when I fixed 2 in place and I permuted the other 4, well, 6 of those also had 1 in place. So I'm also getting a ton of overlap here. So if you remember the inclusion-exclusion principle, which you should, the magnitude of this is not just equal to 24 times 5, obviously. For instance, when we look at the 3-number example, when we add up A1, A2, and A3, we'd be overcounting this middle one by a factor of 3 because it gets included in all of these bubbles, and the same thing is happening here. So in our case, right, when we fix one of these, we already calculated that there's 24 ways to permute the rest of these. There's 5 ways to fix the first element, so 5 times 4 factorial is going to be 120. Then by inclusion-exclusion, we know we overcounted the number of times when we had 2 fixed. So let's fix every combination of 2. How many combinations of 2 are there? Well, there's 5 letters and we're choosing 2. So let's subtract 5, choose 2. And when we choose 2, we permute the other 3 in 3 factorial ways. So we need to subtract this. Now again, by inclusion-exclusion, when we did that, we undercounted the number of ways when we have 3 fixed. And how many ways can we fix 3? 5, choose 3. And the other permutations are 2 factorial. So it's going to be like this. And you just alternate down the line. Now let's fix 4 of them. How many ways can we do that? 5, choose 4. There's one way to permute this. And then we fix all 5. And there's only one way to do that. So we add back the 1. And this is going to give us our final answer. So when we actually work this all out, 5 choose 2 is 10, and 5 choose 3 is also 10. So this is going to be 120 minus 60 plus, this is going to be 20 minus 5 plus 1, and that's going to end up equaling 76. So 76 is the magnitude of this, but remember we need to subtract it from the total to get our number of derangements. So let's take 120 and subtract 76, and that's going to give us 44 total derangements. Therefore, our probability is just going to be the number of derangements, 44, over the total number of permutations, 120, and this simplifies down to 11 on 30, which gives us our final answer. So really the key thing here is just remembering the inclusion-exclusion principle, which I didn't derive the whole thing, but you can find a lot of good videos online about it if you forgot.